Hi listeners, welcome back to our podcast Theoretical Biophysics. I have the pleasure today to interview Yusuke Himeoka coming from University of Tokyo. He's working at the Universal Biological Institute and we by chance came across each other in this beautiful conference in Copenhagen on the quantitative physiology of microbes. So thank you Yusuke for accepting to have this little chat together.
My pleasure. I'm Yusuke Himeoka, Universal Biology Institute. Yeah.
Awesome. So, what would you like to tell us today?
I would like to talk about some theoretical study, mathematical study of bacterial lag phase, stationary phase. Yeah, the sleeping mode of the cell.
Okay. And so, what was your approach to tackle this kind of problem?
So basically, I wouldn't do any experiment, but instead I construct simple, sometimes complicated mathematical model and to understand and sometimes to predict the biological behavior.
Mm-hmm. So what you are writing is, okay, you've got a model of how a bacterial cell works with the elements in it. I think it's good for our listener if we go a bit into the detail of what you consider, and then knowing who's interacting with who, you write a system of differential equations that are coupled together. Okay. Okay, so let's dive in. What do you consider to be inside the cell to explain?
So the first question, should I first explain the title of the paper or something like that?
Well, yeah, we can give the paper where our listener can.
Sure.
Yeah.
Then.
So that was theory for transitions between exponential and stationary phases, universal laws for lag time, and you can find it in Physical Review. So I'll give the link in any case with the podcast.
Cool. Thanks.
Yeah.
So can I just go into the motivation and the model?
Yeah, we follow you.
Oh, sure. The motivation of the study is that first of all, if you grow bacteria, it's kind of tiny microorganism, and they grow like too dense. Like if you put even some cells into the liquid culture, they grow and they reach 10 to 8, 10 to 9 per milliliter. And of course, after growing, they run out all the foods. Then they enter the kind of starving mode, which is called stationary phase. And it is quite interesting phase. Like they are not kind of simply dying because of running out of food. They can kind of bear such kind of harsh condition, and the growth rate is of course very low, and death rate is very low, metabolic activity is quite low, but they are living. That is the stationary phase, or the state of the cells in the stationary phase is called as a dormant state. And the motivation of this study is to kind of mathematically understand what is happening the same kind of phenomenology of the dormant cells. Yeah.
Okay, so what happens to a cell when it is dormant? I see you've got a model of a cell. So
yes, so the key part of the cell growth is the kind of most important part of living things is kind of self-replication, and the molecules which is responsible for self-replication is ribosome and also RNA polymerase. But in this study, I focused on ribosome, and the ribosome is protein machinery which makes protein. And in my model, I put the ribosome and of course nutrient and molecules which kind of stop ribosome working under the nutrient poor condition, and also this protein which is in jargon called as Hibernation Factor.
What's that?
It is also one of the protein.
Okay.
And which forms some kind of ribosome hibernation factor complex to stop ribosome working, and also under the nutrient starved condition, the protein is kind of degraded, but the hibernation factor also protect the ribosome from degradation.
Okay, so you've got two players in the physiology of the cell: those ribosomes that promote growth, and those hibernation factor that blocks it, but also protect it.
Yeah.
Okay, so when the ribosome is bound to this hibernation factor, this occurs when you're on stationary phase. That's right. Okay, I follow you. And this stops growth though, because ribosomes are not anymore efficient. Okay, I follow you.
So kind of this blocking is very important because the ribosome makes itself so kind of such auto-replication, self-replication cannot stop without kind of totally degrading ribosome, or if you degrade all the ribosome, you will never kind of revive from the kind of mutant poor condition. So the blocking without degrading it is quite important.
So you've got these two players actually that are driving the growth or not of the cell.
Yeah.
Okay. And I guess on that you can write some equations.
Yes.
Okay, on the dynamic of those two players. Okay.
So using the ordinary differential equation.
Okay. Okay. And so those ordinary differential equation. Okay, they come here. I see. That's precisely those one.
Yeah, but actually, precisely those four are the equation I used. But the main players are this A and B.
Okay, so you've got one equation for the ribosome, one equation for the
hibernation factor.
What are the two others?
This is substrate.
Okay, so you need food.
But we can, in principle, assume this substrate concentration is constant.
Okay.
And then they can use this substrate concentration as parameter.
Okay, so the substrate is getting into the cell, and this allows the ribosome to work, basically. Okay.
And this C is complex of A and B.
Okay, so you've got this.
So basically, this is kind of different form of A and B. So this is not kind of new player.
Okay, when they are bound together, they form C.
Yeah.
Okay, so you've got this parameterized system where you've got something which allows states to grow or to stop it, and so can we predict anything with this kind of model?
Yeah. Before moving on to the prediction, what I need to explain is that in this model, I suppose that I try to mimic the gene expression, like gene regulation, under the substrate-rich condition. Hibernation factor is not induced. So here the amount of substrate is parameter, and substrate is sufficiently kind of supplied. Almost all substrate goes to ribosome. I mean, the hibernation factor is not induced, but the substrate becomes concentration becomes quite low, then hibernation factor is induced. So this is a very important part of the model.
So that's the signal for the production of hibernation factor. Okay.
And then kind of computing this model numerically. First, this model showed kind of distinct phase of the growth. If you have sufficient amount of substrate, they kind of model grow like happily in a okay speed. But the substrate concentration becomes lower and lower. All of a sudden, like the concentration of hibernation factor exceeds a certain threshold, and suddenly it formed of course, it's gradually forming the complex, but the ratio between the ribosome and hibernation factor exceeds certain threshold. Then most of the ribosome are catched by the hibernation factor, and the growth rate or some kind of activity of metabolism suddenly drops to the low level, and it is kind of but
that's the way where they get into the stationary phase.
Yes.
Okay.
And by doing population dynamics of my cell model, it showed a curve which is very similar to the bacterial growth curve.
I think there is an important point on your work. I mean, this model is parameterized, of course, because you need to have the rate of the chemical reaction, sort of. So how do you parameterize the model?
Yes, because my model is a coarse-grained phenomenological one. We don't have exact parameters in literature, but we can combine some parameters to get the estimate of the parameters. For instance, the production rate of the proteins can be estimated by using elongation rate of translation or something like that. Such parameters I got by combining the real parameters, but still, some parameters are left unestimated. So for such parameters, I kind of try to fit the already known phenomenology by using my model. And I used two phenomenological relationship. The first one is so-called mono equation. This is right. It's called as mono equation, right? The relationship between the
S curve of growth.
Substrate concentration and the specific growth rate. And also the very famous relationship between the growth rate and the rRNA protein relationship.
Okay, so these are really independent experiments from each other. And so, you already estimated the parameters of the model roughly from the literature. But then to make it precise, for instance, especially in the case of E. coli, you take those data of E. coli and you adjust the parameter you already know by order of magnitude to something which is realistic with respect to those data.
Yeah, precisely.
Okay, it's very interesting.
And then,
so now you got a model with 4 coupled equations with parameters that, are estimated and sort of fitted on data. And so what next?
Yeah, so the first of all, at that moment, I published this paper in 2017, and I would say that at that moment, there's no phenomenological model which shows all the bacterial growth phase, which is lag phase, exponential phase, stationary phase, and death phase. But my model shows all the 4 phases. That is one result. And after that, I wanted to predict something. And using this model, I predicted the feature of lag time. First, I need to explain what is lag time.
Yeah, I think our listener will be happy to.
But you are professional.
I am a professional, but I'm asking the questions, not giving them. No, okay. So the lag time is the phase of growth of bacteria. So as we said, a population of bacteria grows, but it actually follows 4 different phases. And in the first phase of growth of bacterial population, what happens when they are put in a new and fresh environment, they don't know yet, it's that the bacteria adapt to this new environment by reshuffling their genetic pathways to be able to better consume the nutrient from this environment. And doing so, actually, they don't divide. It's really the plasticity of the metabolism that they use, which is completely... they are completely focused on that, and they don't really multiply. So they are not yet in phase of growth. So because they are not yet in phase of growth, we call this phase the lag time, which is the time of adaptation for the bacteria in a new environment. And then, as Yusuke said nicely, we've got the growth phase where they divide because of ribosome, etc., and stationary phase where they stop producing those proteins. And we can add also a 4th phase, actually, which is the death phase. Which is when bacteria run out of nutrients or get under stress and they die. On this point, actually, we've got a nice podcast that we recorded recently with Severin Ching. You can check out our Spotify to have more information on this death phase. Okay, Yusuke, so now we know what is the lag phase.
Yeah, thanks. So the very interesting feature of lag time is that the lag time depends on how long the cell starved. Before first of all, there are several ways to enter the stationary phase, but one is the starvation. And if you starve long, the lag time becomes longer. And in a sense, the cell memorize how they were starved. So it is really non-equilibrium behavior. So I'm interested in how the length of lag time is ruled. Then I tried to do a starvation experiment in silico, which means in a computer. So I starved my model. First I grow my cell model in a nutrient-rich condition, and suddenly I impose acute starvation. Suddenly I change substrate concentration to quite low value, and I starved this model cell for a while.
So when you do so, your model, your numerical bacteria, they produce a lot of ribosome complex
hibernation.
Yeah. Okay. So they stock that. This is okay.
So that they produce a lot of hibernation factor compared to ribosome, because the substrate itself is very rare. In a sense, the production rate itself becomes lower. So in absolute value, it is quite low. But comparing ribosome production rate, the production rate of the hibernation factor is quite high. Yeah. So anyway, then during the starvation, because they produce hibernation factor slowly, then they change in intracellular state slowly. And then after a while, I recovered the substrate concentration to the original rich value, and then my model cell starts to regrow again, and I measured how long it takes to this to regrow. That is definition of a lag time in my model. And then I found that of course it is not that surprising, but the lag time increases with starvation time.
Okay, because you got more of this hybridization complex inside you.
Yeah.
Okay.
So, but then I saw kind of function form of the dependency of the lag time to the starvation time.
Yeah.
And what I found that the lag time increases in a square root manner of the starvation time.
Is there any qualitative explanation for why is it a square root or?
Qualitative explanation.
Yeah, I mean, how can we?
Actually,
is it surprising that this is a square root dependence?
Then, well, what doesn't surprise you?
That's a good one.
The linear?
No, I mean, yeah, could be exponential too.
True.
So like a Poissonian process.
But so this became it's difficult to kind of intuitively explain 0.5.
Yeah.
But intuitively speaking, to make either ribosome or hibernation factor, cell needs free ribosome, which is not catched by hibernation factor. Yeah. But basically, under the starvation condition, cell makes hibernation factor. Yeah. So as they produce hibernation factor, it kind of makes much more difficult to make more hibernation factor because hibernation factor catches ribosome. In a sense, the kind of if you make more, it makes much more difficult to make more. This structure typically leads to inverse relationship. I mean, the x dot equal kind of inverse of x or something like that. Okay. And this is the kind of what is happening under the starvation. After the kind of recovery of the environmental condition, what was happening? And then they need to, of course, release the ribosome from the hibernation factor. But I didn't explain, but I have to explain in the model introduction. But in my model, cell grows as they make ribosome because that is kind of necessary part of the cell growth. Yeah. And then after the recovery of the nutrient concentration, they need to make ribosome, but most of them are catched by hibernation factor to kind of dilute the hibernation factor. They have to grow. So it is yes, I cannot tell kind of which exponent this leads to, but you need to do something, you need to do something else in prior to this, but this kind of complicated structure leads to non-exponential power relationship in a kind of mathematical structure. Sorry, this is not that intuitive though.
Yeah, no, it's not intuitive, but I mean, it's super interesting to get into this kind of details.
Sure. And I need to add that this slope 0.5 depends on the stoichiometry of the ribosome and the hibernation factor attachment.
So if you need 2 hibernation factor to stop a ribosome working,
then the exponent will be 1/3. So if this model is correct, it would be great to do very high throughput measurement of the kind of experiment to determine the exponent between the lag time and the starvation time.
Yeah, that would be awesome.
And but this is not that high throughput experiment though. I picked up the starvation and lag time data from literature.
Okay, so some people already measured that. And do you find the 0.5?
What? Kind of.
Yes.
Yes, but
well, I can see. Yeah, I mean, why not?
Yeah.
Yeah.
Yes, but the problem is that this the experimental data is from population level starvation reselection experiment. So it is known that maybe you are much more familiar than me, but the population level lag time experiments sometimes leads to different result to the single cell level lag time experiment. So we should be very careful about the relationship between what my model predicted and what the experimental data in the literature kind of shows.
Yeah, there's always this blind spot, I agree, between having something describing what cells do and actually making the measurement on the population. When interaction between the cells happens within the population, the model doesn't take it into account because it's focused only on the cells. That's a really hard blind spot to take care when you want to have a concordance between the cells. But I mean, on the data you found with respect to this 0.5, I mean, I buy it. So for sure, it must. Phenomenologically, your model works.
Cool, thanks. It's good to hear.
Yeah. Okay. So, would you like to tell us a bit more about
Sure.
the lag?
one,
Yeah,
yeah,
I mean,
so-
yeah, there's some more actually, because you used really those two set of data, which is growth rate versus substrate, which are measured, and ribosome versus growth rate, was it? The Terrewa that.
Oh yeah, tell you what it is.
Yeah,
Here.
yeah, exactly. That was growth rate versus ribosome fraction. And so, okay, those stuff really allows you to get the parameter of your model. But actually, so first of all, your model is predictive, or explaining somehow what happens for the exit of lag phase when you are starved. But so you've got some more insight for another experiment from Nathalie Balaban, right?
Yeah. So I changed it. My model is originally a deterministic ordinary differential equation based model, but I changed the model to the stochastic version using it's very simple, using Gillespie algorithm, which is often used kind of for a stochastic simulation of kind of chemical reaction model.
Okay.
And then I've done the same, like first stir the cell and return the concentration, substrate concentration to reach value, and measure how long it takes that this cell registers growth.
Okay.
And then because I'm using the stochastic model, the lag time has distribution now, and the shape of the distribution, of course, changes how long the cells are stirred. So I measure the lag time distribution at kind of several different points of the starvation, and then I compared the lag time distribution to the lag time distribution data measured by colleagues of Nathalie Balaban, who's kind of really famous person in the lag time and persistent field.
Yeah.
And for some reason, I needed to normalize the lag time distribution using its peak and the full width of half maximum, and then it is a big surprise for me. I didn't expect, but the data and what the model predict collapsed.
So the shape of the distribution
Is quite
holds with your model.
Yeah.
Yeah, I think it's very interesting that swapping from the differential equation is going to give you what happened for the means, but actually, and that's one of the contribution of Nathalie Balaban, I think, which is the most impressive, is that the shape of the distribution is also very, very important, especially when you think in terms of who's gonna get fixed into the population if a stress happen, etc. And the fact that with your somehow very minimal model, you manage to recapitulate all these observations. It's very powerful, actually. I mean, without discussion, and the small background I got from microbiology, I can understand really what you describe for the metabolism of the cell, and the fact that this very simple mechanism explain and holds for such complicated data, actually, I think it's beautiful. It's beautiful because then you can think in terms of this when you think about the cell. That's very impressive.
So the very striking feature of this lag time distribution is that I'm sad that I cannot share the kind of data here.
Go for it on internet.
At the kind of left side of the distribution from the peak is it looks like Gaussian. It kind of decreases as exponential minus x squared.
Yeah.
But the bigger side from the peak, first distribution kind of frequency decrease as exponential x.
Yeah.
But all of a sudden, suddenly the distribution flattened.
Yeah, it's very flat.
It's not kind of totally flat, but it has really, really long tail.
Yeah. It looks like a spike with a very flat tail
True.
Yeah.
But recently, many people started to measure the lag time distribution, and the shape really depends on how you stir the cell. Right? Sometimes it becomes a power law distribution in the tail side. But I don't think my model captured the such kind of dependency of how you stirred the cells. At least my model captured this first Gaussian and exponential with large kind of slope, then flat.
Yeah, and it's very important. I mean, knowing that you've got some lag time which can be very long, but not at a zero value, and that actually those very long lifetime are uniformly distributed somehow.
Somehow.
That's really interesting to know that actually, because I would thought that the more you wait, the less you would have lifetime. It seems not to be the case, and so your model explains that.
Yeah, so it makes it rises so hard, difficult problem, that question that the only way to confirm if this cell is kind of living or not is to plate and ask if it's start to grow, right? And practically you cannot wait that long time. Like for instance, if you need to wait a month, then you judge, okay, this cell already dead. But this kind of super long tail lifetime distribution kind of raises the question that the kind of boundary of the long lifetime and cell death is not that clear.
Definitely. And so you still catch up that the normalized lifetime decrease with an increased value, but as we said, it's almost constant or super low. What is the maximum value that you can reach in that time with your model? I mean,
at least in my model, it can reach quite long time, but
if you've got, for instance, if you want to have, if our listener wants to have a value, what I see is that at 10 to the minus 3 to 10 to the minus 3, basically the lifetime is 30 hours. Normalized lifetime. So 30 something.
30 something.
Yeah. Was 30 times more than the regular lifetime that you see when you watch bacteria. So it means still that if you've got 10 to the 9 bacteria which were starved in the 1 milliliter droplet, you would have 10 to the 6 bacteria that would still be in this super long lifetime.
That would be true, but this is maybe this is probability density distribution, I think. So the kind of the number of cells waking up in this period is 10 to minus, say, 3 multiplied by the width of this bin. So it's much less. Yeah.
Okay, got you. But it's still, if the bin is size 1.
Yeah, kind of.
Yeah.
Then.
In between 29 and 30. Yeah.
That's true, yes.
Yeah, that's quite a lot. It's quite a lot. Okay. And so what are the perspectives for this work? Did you have any follow-up on this?
What I'm kind of working on currently is that I like this model, but this is simple, coarse-grained, but I designed this model to show this interesting behavior. So we cannot tell how this emerged from the real gene regulatory network or metabolic network or something like that. So my follow-up research is ongoing still, but I want to say simply derive this model from the realistic ones. So and
okay. Well, I think it's time for us to wrap up. It was a really interesting discussion. Cool. Thank you for taking time.
Thanks for having me.
Yeah, it was awesome. And so, listeners, it was a pleasure to have you one more time on our podcast. I will add a lot of links to follow up on the work of Yusuke if you want to have a look at these papers. And see you for a next record.